Hello everyone and welcome to this lecture in about Chapter 2, Basic Concepts in Power System Analysis. Here you can see the sub-chapters in this chapter, and I will talk a little bit about 2 single-phase AC circuits, 2 3-phase AC circuits, and 2 4 per unit quantities. Of course, the other sub-chapters you can go through on your own. Here you see a sinusoidal function as a rotating vector, and that's typically how we represent it when we analyze it. So we have a vector that is rotating with angles as it rotates. The basics of analysis in the power system is, of course, these elements of resistance, inductance, and capacitance. We'll come back to that. As I said, we're working on AC circuits with steady state, and it's a pure sinusoidal and of constant frequency. Phase representation, as I said, or sinusoidal voltage and currents is what we are using mainly here. Of course, capital letters we often denote with large capital V and I. I will have some also using capital U, but this is changing depending on literature you are using. Typically using the italic lowercase letters V, I, and P for power, for indicate an instantaneous value. So let's start with the resistance. It's a typical symbol for resistance, so we typically apply a current as a sinus function with the amplitude denoted like this. Then you have a voltage drop over the resistance times the current. And here you can see how the sinusoidal function will look at over this resistance. So you have the current and the voltage, and what you can see is, of course, they are in phase with different amplitudes. And here over to the right hand side you can see how the vectors representing these instantaneous values can look. Of course, if you look at the impedance over resistance, we can use those values, and you can see that the angles will delete each other, and you have the resistance R is equal to Z. You could also work RMS values, because that's values you are using in the when you measure, and it will come out with just the same way. For the inductance, we know that the voltage is the inductance times the derivative of the current, and then we have a cos function coming out of the derivative. We can use then this type of trigonometric relationship, and we will have an expression for the voltage, instantaneous voltage, looking like this: XL times I, or U, maximum U, times sinus. And then we have this 90-degree angle between the voltage and the current. And you can see here also then that actually in the inductance, where we have the voltage is actually leading for the current, and you can see the voltage is coming down, hitting then this axis before the current, 90 degrees. And in vector format we can look like this, and we have then the positive ways rotating toward this way. And of course the impedance, if you have the expression for this, we will have this expression, and this XL is the ohmic value, as you know, from the inductance. But we will typically use it in this fashion, or in JXL fashion. For capacitance, we can have similar approach. We have a current and a voltage drop, and over here the voltage will then be the integral of the current, as we know, and we will get out a cos function in the end. We can then, at the same way as in inductance, use some trigonometric relationship, and we can finally get an expression looking like this, where we have the minus 90 degrees. So for the capacitance, V is opposite as the pure inductance. So now the current is then hitting the axis 90 degrees before the voltage, so the current is leading the voltage. And on the right hand side you can see, of course, how that will look in the vector format. It's the same way we can have an expression for the impedance looking like this. And typically when we calculate vector format, we will have expression like looking like this, or in the imaginary values like that.